Hi everyone, and welcome to your Energy Sources or Metabolic Substrate lecture. My goal with these lectures, generally speaking, are to try to keep them as close to 20 minutes or under. Some topics go a little longer, so they'll just need a little bit further exploration. But if I'm going a little quick, always feel free. Obviously, it's video. You can go back and rewatch things. Or after you're done a bit more diving into the topic, such as reading your textbook, then by all means send me an email and I'm more than happy to set up some office hours and we can discuss things then. Additionally, this is a good cue, I just wanted to let you know for today's lecture, I am in downtown Montreal and it's very hot, so I have to have the window open. So there might be some background noises. So I apologize if you have headphones in and a motorcycle or something goes ripping by. We'll try to cut those out as best I can without interrupting the flow of the lecture. Last point with this is, again, your textbook. I want to thank the publisher Wolters Kluwer for providing a lot of the text information and images. Again, your exercise phys textbooks are great, and appreciate them providing the foundation for my lecture and to be built on. Okay, without further ado, let's get into it. So again, metabolic substrates. What is it? What's going on here? Well, ultimately, it's where we get our energy from to do what we do day to day. And when you think about the world as a whole, we really have one main source of energy, and that's the sun. Okay, so the sun obviously has light energy or electromagnetic radiation that it sends to the earth, and from that, plants can take that energy, convert it into stored energy. We'll pause on that for a minute. There's lots of types of energy that we come across in the world: electrical, heat, mechanical. Mechanical is obviously something that's getting moved physically. And I think most important for us is the chemical energy stored in chemical bonds between atoms. And the reason for that, again, as I already alluded to, is plants take that energy from the sun, they store it in the chemical bonds in themselves, and we can then take that energy through those chemical bonds and use that to put to work for our own bodies. And that is metabolism, or as some refer to it as bioenergetics, is taking food, using that energy to do work. Okay, it's that process. All right. So let's take a look at three, and we already are aware of them most likely, types of metabolic substrates or sources of fuel, right? Food fuel that we turn into energy. That's carbohydrates, fat, and protein, right? We can see some diagrams here of their chemical structures, and before you see these chemical schematics and heart rate starts increasing if you're not a chemistry person, it's okay. All these are structures to help explain their function, and that's going to be a huge theme throughout the whole class, especially when we start speaking about the biochemistry of how our body works, or the physiology. Structure is function. That should be the catchphrase for all of biology, really. So ultimately, we have three, again, carbs, fat, and protein. They're also called macronutrients, and the idea behind that is, again, it's where we get our energy from, okay? So different types, we have sugars or simple monosaccharides. We have di, meaning two, or poly, meaning many saccharides, and that's another word or more specific word for carbohydrates. Fats, we can have saturated or unsaturated, and we'll explain exactly what that means when we further explain fats. And proteins, last but not least, are comprised of amino acids, or the building blocks for proteins. Okay, diving into carbohydrates. As I mentioned, plants take in their energy, they make the carbohydrates primarily that we get, and the great thing about carbohydrates, in particular simple sugars, is it's energy that's readily available. It's ready to be used by the cell. No processing needed for monosaccharides, okay? But even disaccharides, so two saccharides or two of these sugar rings, are also fairly easy to absorb. We'll get into why in a moment. And then polysaccharides are stored versions of these. Okay. So monosaccharides, let's explore those a little bit first. So 6 carbon rings molecule rings. So you just have this ring structure. Again, it's an oxygen, but they're linked with an oxygen to varying degrees. So with these carbon rings, you can think of them as just the foundation structure for saccharides. So it's like the building block for all the other saccharides or carbohydrates is this one ring. Okay. So as I mentioned, we can join these rings together. And that's exactly what a disaccharide is. There's two. And why I was saying these are fairly readily used by the body is because all there is one bond between the two. So if you can think of monosaccharide being very easily used for energy just as it is, if you have two together with one bond, we'll find that it's relatively easy to split that bond. So now again, we have readily available energy to be used in this form of carbohydrate. Now the last and perhaps one of the more interesting ways that we store glucose in our body, so a monosaccharide, glucose, is glycogen. And this is going to come up a number of different times later in the course. You're going to hear glycogen storage, intramuscular glycogen storage. And all it is these single building blocks of carbohydrates or monosaccharides joined together into this, it looks like a bit of a higgly-piggly mess of glucose molecules. Okay. Now, the great thing about this is its structure. So it's built, there's lots of space in and around each of these glucose chains or polymers of glucose molecules. Again, this is a polysaccharide, meaning many saccharides or many sugars put together. With that, we're going to find that enzymes, so the thing that breaks these chemical bonds for us, can get in there a little easier than if it was in a different structure. So glycogen is in animals, and in particular muscle and liver, but cellulose is another polysaccharide, but it's for plants. And the way plants set up the structure of this is called cellulose, and they end up stacking quite straight and in rows. And what happens between those rows is something called hydrogen bonding. So they stack kind of layer on layer of these polymer chains of saccharides. Now, the interesting thing about that for us as humans is when we eat plants with cellulose, we call it fiber. And our bodies can't digest or use those chains of polysaccharides for energy. And the reason is those enzymes, the things that we use to chop off little single units of glucose, can't get in between the structures in cellulose. So, animals like cows, for example, actually have bacteria that start breaking down that cellulose to be able to get into a format that they can then digest with their own enzymes. So, yeah, some fun facts about cellulose and glycogen. When we're, so getting back to our own bodies, glucose is that simple unit, and a lot of us would refer to glucose free floating in the blood, ready to be used or pulled into cells for energy as blood sugar. Okay, so it's a simple sugar, it's the monosaccharide. We've mentioned that a few times. Glycogen, you're just introduced to that. That's the chain or the storage form. Now we can't use the whole molecule of glycogen as energy, it's just storage. So we have to chop off each of those little monomers or monosaccharides to be able to be consumed, and it kind of gets transported around the body that way, okay, as we need to use it. And so we have this freeing of, or let's start the other way. So we have the building of glycogen through this process called glycogenesis. So genesis or generating, you can think of those two words as very similar. So forming glycogen. And then of course when we need to, after we've built up the storage unit, we got to chop off the parts that we need, and that's called glycogenolysis. And this will come up a lot, this kind of end phrase or suffix of a word called lysis. Lysis means chopping or cutting. Or in some cases, cell lysis is the whole cell exploding. So it's kind of coming apart. Anytime you see lysis at the end of the word, think something's getting chopped. Okay? All right, so why are we talking somewhat at length about glycogen and glucose? Well, it's one of the most important, readily available, and usable energy sources for our body, both during exercise and rest. We also have two other, right? So we covered carbohydrates, but we have two other sources of energy for our body. So one of them is fat. And we know, typically, I believe, most of us commonly know that we have fats and we use that for energy. A lot of the time it's stored, typically as visceral fat or fat on our bodies, but, like adipose fat, or sometimes visceral fats, like in and around our organs for protection. But when we're thinking about it for energy use anyways, we know that these big long chains that I showed you earlier of fats can be metabolized. So they're kind of broken up and again used for making energy for ourselves. We have two types. One's fatty acids and the other is triglycerides. So we'll find that fatty acids are the metabolized, capable, or ready format of fats, and triglycerides are more the package, similar to glucose and glycogen, just for fats. Okay. So let's take a look at their structures again. Structure equals function. In this particular case, we'll look at saturated. There's also unsaturated fats. You might have heard of this when you're talking about different foods, saturated fats, polyunsaturated fats, omega-3s, omega-6s, and we'll explain what that is. But ultimately, here's the structure of a saturated fatty acid. And all that's saying is that every single one of these carbons has every possible one of their available bonds, the chemical bonds they can make, filled with hydrogens. Okay? So what ends up happening is, even in a 3D perspective of this molecule, it comes out to be fairly straight. You see this kind of straight, long length of carbon chain of a structure. Okay, this is just a functional group on the end, which just means it's kind of can react in different ways. And here's the tail. So this whole structure is a stearic acid, is really common, 18 carbons, and most saturated fats come in even-numbered carbon chains. Okay? Now the big key feature here is there's no double bonds. And just to refresh you as to why or how that's happening, carbons can have 4 bonds total. So if we look at, let's just say this one carbon here, you can say that's 1, 2, 3, 4. Okay, so that's available. Now, if there's not a fully saturated carbon chain with hydrogens, we get unsaturated fatty acids. And one of the best examples, just to start looking at unsaturated fatty acids, would be right here. We notice that there's a double bond. So because the carbons share an extra bond versus having them attached to hydrogens, they have a double bond. Okay. And then we can have polyunsaturated too, so that means more than one double bond. Why do we care? What difference does it make whether fats are saturated or unsaturated? Huge. So unsaturated fats are commonly thought to be much more healthy for us. Why? Well, when they're packed together, and we'll see how that happens when we get to our storage with triglycerides, but when they're packed together, if they have a straight structure, they tend to be packed together fairly close. And again, as I mentioned before with the glycogen, it's harder for enzymes to get in this 3D space to be able to start chewing off or lysing off different components of the carbon chain for metabolism. What's easier to metabolize is these fatty acids with double bonds. And the reason for that is, instead of having a very straight structure, they actually end up bending or having a kink in their structure. So when you start stacking together, let's say, I can't make my finger bend the other way, but if you have different fatty acids with various double bonds, they're going to stack slightly farther away. And even if they're relatively close together, parts of their tails are still going to be more readily exposed. So again, with this 3D structure, it's kind of, you need to conceptualize that in your head a little bit. We find that they're more readily metabolized. Okay. So again, triglycerides are the storage form. Fatty acids, or free fatty acids in particular, are fatty types of fat that our body can go through lipolysis. Lipo just means fat, so lipid lysis, chopping. Okay, so metabolizing that for energy. Again, that's in the muscles or the liver primarily, but again, here's the structure. So having these 3 fatty acids, meaning 3, triglyceride. This is a glycerol molecule here in the purple. These are just the water molecules that essentially go through a dehydration reaction to form our triglyceride here and water. Okay, so you can see when we have this triglyceride here, which is the glycerol attached to 3 fatty acids, if they're just linear, fully saturated fats, it stacks quite evenly. Hopefully you can picture in your mind, as soon as those double bonds come, the triglycerides kind of crimp and kink away from each other, again creating more space, being more readily metabolized. Another thing with that comes with plaques that build in our arteries. Again, if it's not packed so tightly, it's easier to clean out. Okay. All right. Carbohydrates, fatty acids or fats. Last but not least, proteins. Well, in a way, least, and here's why. So our bodies really avoid metabolizing protein. Okay? Their key go-to energies: carbohydrates, then fats. Proteins tend to only be metabolized under a fairly deprived or starved state of energy. Okay, the reason for that is it's very cost effective to metabolize protein. Also, is our bodies just don't want to do that, right? Our muscles are made of protein. We want to keep the structures that we built. It's very cost ineffective if we start chewing up muscle to do that. So what are proteins? Well, they're essentially a series of attached amino acids. So our amino acids are the building blocks. Proteins are these big long chains of amino acids. And we can build all sorts of things in our body with proteins. So they are made primarily for structure, but again, can be metabolized for energy in an emergency. All right. Now, if we think of people who only eat plants, we know that they can do so because there's proteins in there. And the reason that's an issue is because there are 9 essential amino acids. So there's 9 of these building blocks of proteins that our bodies can't make, so we have to consume. So for those that are omnivorous, so we eat plant and animals, a lot of our protein will come from plants. And so we take in these essential amino acids that way. For vegans or vegetarians, they can as well. Sometimes it's a little more complicated. You just need to make sure that you're getting the right complementary fruits and primarily vegetables in order to supplement these 9 essential amino acids. Okay? There are non-essential amino acids, which doesn't mean they're not necessary. It just means our bodies can produce them. And the key feature to that is it's still good to take them in through nutrition, but again, if our body needs them, we can make them based off of what we have in our body. Now, the structure of amino acids, the name somewhat gives it away. There's an amino group, or a section of the molecule. There's an acid group, which again we'll explain in a second. But there's also this R chain, or this chain of carbons with a functional group on it. I haven't spoken too much about functional groups, but essentially they're a commonly arranged set of atoms that will produce a certain reaction or chemical reaction fairly readily, depending on what that configuration is. So, so different amino acids will have different reaction groups or structures based off of that. So we'll look here, again, the amino group essentially just has a nitrogen as its backbone rather than a carbon. And this acid group, you might have seen this in a few other illustrations so far, is just set up to be able to donate a proton or accept it. And again, the protein chain tends to happen along this nitrogen acid group. So you kind of get this reaction, I don't want to go into too much detail for you, not a chem class, but essentially go through these reactions that allow long chains of amino acids to link up. And then you have all these side groups that allow different functions of these proteins to occur, or different structures. So, with chains of proteins, again, obviously we can build things with these. We can use amino acids for metabolism and for energy, but ultimately our end game with protein is to try to build stuff with it. One of the most important, and it's important for metabolism, one of the most important protein structures that we'll talk about 100% is enzymes. Okay, so enzymes have this long thread of amino acids all linked together. But the interesting thing about that is they'll fold back in and kind of create this 3D structure. Okay, so you can think of it as a blob, like a thread zigzagging all together that conforms into a very specific structure based off of the amino acids there. It's amazingly brilliant and beautiful science, biology. It's mind-blowing. If this kind of wows you, this idea that a string of these with certain functional or side groups just knows how to form a very specific 3D structure, biochemistry is your jam for sure. But I digress. So enzymes are proteins, long strings of amino acids, and what happens with their 3D structure is they create these little pockets. Now those pockets are very specific locks. You can think of them as like a lock in a door. And the key is the substrate or the thing that fits into that pocket. Now within that little area, what ends up happening is a very special environment occurs, both through the structure, but also sometimes even the let's say, chemistry in there. And it allows certain bonds to either be broken or built up with a lower amount of energy input. So here's the other kicker about biology in general. Biology loves being lazy. The least amount of energy that it takes to do things is ideal. Our systems, organisms are all set up to be very energy efficient. If something is energy costly, typically there's a very good reason for that. It usually has to do around mating and reproduction. But aside from that, it's very rare that any biological process will happen that's energy expensive, that serves a basic function. Okay? So again, back to enzymes, this little pocket or this keyhole of 3D structure, right? It's a 3D twine sort of structure, okay? Okay, so it doesn't, it won't make a reaction happen, but it creates the scenario where it'll happen more easily, so it happens quicker. All right, these reactions, again, either building or taking apart, occur more quickly. So it happens faster, the rate at which it happens. Now we'll look at a couple of different, a number of different, 3 in particular, energy systems in our bodies, and they happen over multiple steps, okay? We're going to talk about glycolysis later. It happens over 10 steps. Now at each step there's enzymes to help out. There's always one that's going to be the slowest, and that enzyme's called the rate-limiting enzyme, okay? So when all the substrates get to this point, it won't be able to go any farther until it gets to the enzyme to get moving forward. And there's, if ever there's a backlog, it'll happen at the rate-limiting enzyme. Okay. All right. So again, just to help with that 3D structure kind of concept, you have a substrate. So let's say glycogen coming into this enzyme. This enzyme will see the glycogen and it'll want to lyse or chop at a certain point, but to do so it'll just help form a structure. It forms a very specific 3D pocket for that glycogen to come in, and then it will help lower the energy or activation energy that is needed to cause lysis, or that dehydration or hydrolysis, of that part. So the 2 parts, monosaccharides, come apart essentially. Okay. So what do we call this when it's either things are getting built together or pulled apart? They have specific names. I've been avoiding using them because we haven't gotten to this point yet. But we have a catabolic, which means to break apart, and an anabolic, which means to build. If you ever kind of forget, you can think anabolic steroids. You use that to get really built up. So building is anabolic, catabolic is breaking down. Okay. Now, if you see enzymes with the name of A's at the end, usually that means it's a catabolic enzyme. Okay. Great. There's this interesting effect, and we'll be a little brief over these last 2 points, but again, this mass action effect is this thing where if you look at this A plus B into AB sort of equation, what it's saying is there's this equilibrium for a lot of substrates in our bodies. So, and it's based off of concentration. So if you have a lot of A and B, it's going to want the enzyme and the flow of the reaction is going to want to go to build lots of AB. That being said, if you have lots of AB, it'll find different paths to another enzyme, which will want to be A and B separately. Okay. Now, in order to do these reactions, there's certain things that modulate it or control or help control. And one of the things, again, with that 3D structure is just changing the structure of the enzyme. When the change of the structure of the enzyme occurs, what happens is the capacity or the specific pocket that's created by that 3D structure changes, and then it can no longer work, or it won't work as well. Usually it stops working very well. And one of the things is coenzymes. So a lot of vitamins, minerals potentially help form the final shape of these enzymes. So vitamin B, a lot of B vitamins are used in energy, and so a lot of the enzymes used for producing energy need these coenzymes of B vitamins, depending on which one you're talking about. Other things are temperature and acidity. So one of the best examples of this is, we'll go into depth what acidity and pH is later, but if you have something, there's this pH and it's a scale, 114. So neutral is 7, something that's very acidic would be a 1, something that's very basic, 14, and that just helps us understand the environment or how much hydrogen or protons are in a certain area or solution. Okay, again, we'll dive into that a bit more. So the more acidic, think of something like lemon juice, it's going to have lots of hydrogen protons around. Okay, so to give you an idea, our bodies tend to sit around 7.4. So that's very close to neutral. Perfectly neutral is about 7, pH is 7. So with this kind of balance between of hydrogen protons that are free floating versus not, if we happen to get more, and this happens with exercise, we'll come across this in our next segments, it'll become more acidic. So when something becomes more acidic, the number drops down, so it goes from 7 to 6 to 5 to 4. So what happens there is the enzymes again start changing shape. And what happens is they don't become very, I was going to say useful or productive, okay? They don't have that pocket anymore. Temperature does a similar thing, right? You start exercising, you get hot. Again, those enzymes change shape. And part of that comes from a shift in pH. So once our temperature changes, that'll change the pH in our bodies. And so you get this double effect that occurs, and this Bohr effect is a shift. This is an example using our blood and oxygen carrying capacity. So if we have our pH, here's neutral, our lungs just naturally are a little bit more basic than our periphery, so like the blood in our hands. And what that does is makes oxygen want to bind to our blood more readily when it's in the lungs, and unload and get off of blood when it's out in our periphery, which is a good thing in this case. But when we're exercising and it happens at a systematic level, it's less good. Okay, so today in this segment we covered carbohydrates, fats and proteins, and enzymes, and how they work and their foundation, in particular with a focus on structure and function. Cheers.